Does true nothingness exist, or does the universe refuse to allow absolute zero in any corner of space? Even when every particle is removed, quantum field theory predicts a baseline called zero-point energy, a ground state that does not vanish. Tonight, we step directly into the quantum vacuum, where fields remain present even without atoms, where measurable effects like the Casimir force and the Lamb shift prove that empty space is not empty at all. Stay with me as we enter "If nothing means zero, why can't physics make the energy exactly zero?" and begin by defining what physics is truly allowed to call nothing. If nothing truly means zero, then why does the universe refuse to let empty space rest at exactly zero energy? Even if every atom were removed, every photon absorbed, every particle annihilated, modern physics predicts that space would still retain a baseline energy known as zero-point energy. This is not speculation. It arises directly from quantum field theory, the framework that underlies the Standard Model and describes electrons, photons, quarks, gluons, and the Higgs field as excitations of deeper fields permeating space. To understand why nothing cannot equal zero, we must first clarify what physics allows the word nothing to mean. In classical physics, nothing is straightforward. Remove all matter and radiation from a region, and what remains is empty space. In Newtonian mechanics and Maxwell's electromagnetism, fields can exist, but if they have no sources and no waves traveling through them, their energy can be defined as zero. The vacuum in classical theory is a silent background. It carries no unavoidable energy. In that framework, zero means zero. Quantum theory changed that foundation. In 1925 and 1926, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac developed quantum mechanics, and one of its central features was uncertainty. The Heisenberg uncertainty principle states that certain pairs of physical quantities cannot both be known with arbitrary precision. Position and momentum form one such pair. Energy and time form another. Mathematically, this principle prevents a quantum system from having both perfectly defined energy and perfectly static behavior. Even in its lowest allowed state, a system cannot be completely motionless. Consider a simple example that physicists use to build intuition: the quantum harmonic oscillator. Classically, a mass on a spring can sit at rest at its lowest point, with zero kinetic and zero potential energy. Quantum mechanically, the same system has a lowest energy equal to 1/2 of planned times its angular frequency. This non-zero ground state energy is not optional. It follows directly from the structure of the Schrödinger equation. If one attempts to force the energy to zero, the uncertainty principle is violated. The lowest state is not absence. It is a constrained minimum. Quantum field theory extends this principle to every point in space. Instead of a single oscillator, each mode of each field behaves like a harmonic oscillator. The electromagnetic field, for example, can be decomposed into independent modes, characterized by wavelength and polarization. Each mode contributes an energy of 1/2 omega in its ground state, where omega is the angular frequency. Summing over all modes leads to an enormous formal energy density. At first glance, this appears catastrophic, but here, careful reasoning enters. Physicists do not measure absolute energy. They measure differences. In most non-gravitational contexts, a constant shift in energy does not affect observable predictions. The formal infinite sum is handled through renormalization, a mathematically consistent procedure developed in the 1940s by Julian Schwinger Richard Feynman, Shinichiro Tominaga, and Freeman Dyson. Renormalization removes unobservable infinities and leaves finite, testable corrections. The baseline remains conceptually present, but its absolute value is not directly measurable except through gravity. This distinction between ground state and absence is essential. In quantum field theory, the vacuum state is defined as the lowest energy configuration of all fields. It contains no real particles, meaning no excitations that can be detected as free quanta. Yet the fields themselves remain. The electron field, the photon field, the gluon field, the Higgs field, these do not switch off when particles disappear. They settle into their minimum energy configuration. Empty space becomes a physical state of fields, not a blank void. Evidence for this baseline is indirect but precise. One example comes from the Casimir effect, predicted in 1948 by Hendrik Brugd Gerhard Casimir. When two conducting plates are placed extremely close together, on the order of micrometers, the allowed electromagnetic modes between them differ from those outside. The difference in zero-point energy densities produces an attractive force. In 1997, Steve K. Lamoureux performed a high-precision measurement confirming the effect within a few % of theoretical prediction. Later experiments refined the agreement. A force emerging from altered vacuum modes is difficult to reconcile with the idea of absolute emptiness. Another example is the Lamb shift, measured in 1947 by Willis Eugene Lamb and Robert Curtis Rutherford. They observed a small energy difference between two hydrogen energy levels that the Dirac equation predicted to be identical. Quantum electrodynamics explained this shift as arising from interactions between the electron and vacuum fluctuations of the electromagnetic field. The correction was tiny, on the order of 1000 MHz, but measurable with microwave spectroscopy. A subtle deviation in atomic spectra forced a revision of what empty space contributes to atomic structure. NASA and ESA observations reinforce the broader framework in which these calculations sit. The Standard Model, confirmed repeatedly at facilities such as CERN's Large Hadron Collider, depends on quantum field theory's vacuum structure. The discovery of the Higgs boson in 2012 demonstrated that the Higgs field has a non-zero vacuum expectation value of approximately 246 giga-electron-volts. This constant background value gives mass to elementary particles through spontaneous symmetry breaking. Even in the absence of particles, the Higgs field maintains its ground state configuration. Without it, electrons would be massless and atoms could not form stable structures. One might ask whether zero-point energy can be extracted as a power source. This idea appears frequently outside mainstream physics. The answer is grounded in thermodynamics and field theory. The vacuum state is the lowest accessible energy configuration. To extract energy, a system must transition to a lower state. If no lower state exists, there is no reservoir to tap. The zero-point energy is part of the baseline definition. It cannot be mined without redefining the vacuum itself. This constraint preserves stability. Ordinary space does not radiate away its baseline energy because there is no permitted transition downward. A useful everyday comparison involves temperature. Absolute zero temperature, 0 Kelvin, represents the lowest thermal energy accessible to a system. Yet even near 0 Kelvin, quantum motion persists. Superfluid helium, cooled to a fraction of a Kelvin, still exhibits zero-point motion. The atoms do not freeze into complete stillness because quantum constraints forbid exact rest. In a similar way, The quantum vacuum represents a state with no excitations, but not with zero field amplitude in every respect. The analogy is not perfect, but it anchors the intuition. Another compelling line of reasoning comes from cosmology. Observations by ESA's Planck satellite and NASA's Wilkinson microwave anisotropy probe measured the cosmic microwave background with extraordinary precision. The large-scale uniformity of the universe depends on quantum fluctuations stretched during cosmic inflation. Those primordial fluctuations originated from vacuum fluctuations in the inflaton field. Their imprints remain visible as temperature anisotropies at the level of 1 part in 100,000. Structures of galaxies trace back to fluctuations that began in what would otherwise be labeled vacuum. This does not imply that the vacuum is a chaotic sea of particles popping in and out in a literal sense. That language can mislead. The mathematical formalism describes correlations in fields. Virtual particles are bookkeeping devices in perturbation theory. What is measurable are shifts in energy levels, scattering amplitudes, and force corrections. These are calculated through Feynman diagrams and confirmed experimentally. The vacuum is active in the sense that it contributes calculable corrections, not in the sense of visible sparks. A deeper tension appears when gravity enters the discussion. General relativity, formulated by Albert Einstein in 1915, responds to energy density. If the vacuum has energy, it should gravitate. The cosmological constant term in Einstein's field equations acts like a uniform vacuum energy density. Observations of the universe's expansion indicate a small but non-zero value associated with dark energy. Yet naive quantum field theory estimates exceed the observed value by many orders of magnitude. This discrepancy remains one of the most significant unresolved issues in theoretical physics. What then qualifies as proof that the vacuum baseline is real? Not direct observation of zero-point energy as a fuel source. Instead, proof emerges from cumulative consistency. The Lamb shift matches quantum electrodynamics. The Casimir force matches mode calculations. Precision measurements of the electron's anomalous magnetic moment agree with theory to parts per trillion. The Higgs field's vacuum expectation value explains particle masses. Cosmic microwave background anisotropies align with inflationary models seeded by quantum fluctuations. Each result alone might be debated. Together, they form a coherent structure. Returning to the starting point, classical emptiness allowed the possibility of absolute zero energy. Quantum theory removes that option. The lowest state permitted by the mathematics carries unavoidable energy contributions. This is not decorative language. It follows from operator algebra, commutation relations, and experimentally confirmed corrections. The ground state is defined relative to excitations, not relative to philosophical absence. Nothing, in quantum physics, is the absence of particles, not the absence of fields. This distinction reshapes how atoms, space, and the universe are understood. Atoms exist because electrons occupy quantized states influenced by vacuum corrections. Space is not a passive stage, but a configuration of interacting fields. The universe evolves from fluctuations that originated in vacuum states. The Higgs field demonstrates that even mass arises from a non-zero background configuration. Absolute zero energy becomes unattainable, not because nature resists simplicity, but because the structure of quantum law forbids it. One final reflection stays within experimental bounds. If absolute zero energy were possible, the mathematical structure of quantum field theory would collapse into classical determinism. The uncertainty principle would fail, atomic spectra would differ, Casimir forces would vanish, the Higgs mechanism would require reinterpretation. Observations across laboratories and space missions contradict that scenario. The refusal of energy to reach perfect zero is not an anomaly. It is the signature of a quantum universe. And as the vacuum shifts from emptiness to structured ground state, the next step presses forward. If particles are merely excitations of fields, what exactly remains in space before any particle appears at all? If every particle were removed from the universe, what would remain in space? Modern physics answers this without hesitation. Fields remain, not as metaphor, not as mathematical decoration, but as the primary ingredients of reality, according to quantum field theory. What we call particles are localized excitations of those fields. When the excitation disappears, the field does not vanish. It settles into its vacuum state, its lowest energy configuration. The meaning of emptiness changes at that point. To understand this clearly, the word field must be defined in plain language. A field is something that assigns a value to every point in space and time. Temperature across a room forms a familiar example. At each location, there is a number representing how warm or cool that spot is. The temperature field exists whether or not anyone stands there to measure it. Similarly, Earth's gravitational field assigns a gravitational acceleration to every location around the planet. That field persists whether an object is falling or not. In classical physics, fields describe forces. In quantum field theory, fields describe matter itself. In the early 20th century, Paul Adrian Maurice Dirac proposed that the electron should not be treated as a tiny billiard ball, but as a quantum excitation of an underlying electron field. Later developments extended this idea. The photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. Gluons are excitations of the gluon field. The Higgs boson, discovered in 2012 at the Large Hadron Collider operated by the European Organization for Nuclear Research, is an excitation of the Higgs field. The fields are primary. The particles are temporary patterns within them. This shift in perspective becomes unavoidable when examining experimental evidence. In scattering experiments, such as those conducted at the Large Hadron Collider, particles collide and transform into other particles. The underlying conservation laws are expressed not in terms of individual objects, but in terms of symmetries of fields. Spin, for instance, is not a literal rotation of a tiny sphere. It is a quantum property, emerging from how a field transforms under rotations in spacetime. Electrons possess spin 1/2, not because they spin in the everyday sense, but because the electron field obeys mathematical relations tied to the structure of spacetime itself. Why do fields not disappear when particles do? The reason lies in how quantum field theory is constructed. The equations defining a field do not depend on whether excitations are present. The electron field exists throughout the universe. If an electron is created, it corresponds to a localized disturbance in that field carrying specific energy, charge, and spin. When the electron annihilates with a positron, the excitation vanishes, often converting into photons, which are excitations of the electromagnetic field. Yet both underlying fields continue to exist. The field is not the particle. It is the medium from which the particle emerges. A useful comparison can be made with the surface of the ocean. The ocean exists whether or not waves are present. A wave is a temporary pattern traveling across the water. When the wave subsides, the water remains. In quantum field theory, however, The analogy must be handled carefully. The ocean is made of molecules. Fields are not made of smaller components in the standard model. They are fundamental entities. Still, the comparison helps clarify why excitations can appear and disappear without eliminating the underlying field. Observational cosmology provides further confirmation of this picture. Measurements of the cosmic microwave background radiation by the National Aeronautics and Space Administration through the Wilkinson Microwave Anisotropy Probe and by the European Space Agency through the Planck satellite reveal tiny prosophiae, fluctuations in temperature across the sky. Those fluctuations correspond to density variations in the early universe. The prevailing model of cosmic inflation attributes those variations to quantum fluctuations in fields during an early phase of rapid expansion. These were not particles in the ordinary sense. They were fluctuations of fields in their vacuum state, stretched to astronomical scales. Galaxies trace their origin to field behavior in what would otherwise be labeled empty space. The Higgs field provides a particularly concrete example of how emptiness acquires structure. Unlike the electromagnetic field, whose vacuum expectation value is zero in the absence of excitations, the Higgs field has a non-zero vacuum expectation value throughout space. This means that even when no Higgs bosons are present, the Higgs field maintains a constant background magnitude. That background gives mass to elementary particles through their interaction with it. Electrons, quarks, and other fermions acquire mass proportional to how strongly they couple to the Higgs field. Without this ever-present field, atoms could not exist in their stable form. The term vacuum state, therefore, does not mean a region stripped of structure. It means the configuration of all fields corresponding to minimal energy consistent with quantum constraints. In that state, no free particles are present, yet the fields retain defined properties. The electromagnetic field has zero average electric and magnetic field strengths, but still exhibits quantum fluctuations. The electron field has zero excitations, but still obeys its field equation. The Higgs field maintains its background value. Emptiness becomes a precise configuration, not an absence of reality. One might wonder how we know fields are not just convenient mathematical tools. The answer lies in predictive power. Quantum electrodynamics calculates the anomalous magnetic moment of the electron with extraordinary accuracy. Experiments measure this value to many decimal places, and the theoretical calculation, based on field interactions including vacuum fluctuations, agrees within parts per trillion. Such precision would be unlikely if the framework were merely symbolic. The fields encode real physical behavior. Agreement at that level reinforces the interpretation that fields represent genuine aspects of nature. Space, in this framework, is not a stage separate from actors. It is interwoven with fields that fill every region. Even in intergalactic space, where the density of atoms can fall below 1 particle per cubic meter, the electromagnetic field, the neutrino fields, the quark and gluon fields confined within hadrons, and the Higgs field remain present. The vacuum state describes their lowest energy arrangement. Remove all particles, and what remains is not nothing. It is a structured ground configuration. The James Webb Space Telescope has recently observed galaxies at redshifts corresponding to times when the universe was less than 1 billion years old. These observations depend on models of atomic transitions and field interactions that assume the persistence of fundamental fields across cosmic time. The spectra of distant galaxies match predictions derived from quantum field theory. Hydrogen emission lines appear where expected. Fine structure splittings correspond to calculations involving spin and electromagnetic interactions. The consistency across billions of years implies that the same fields pervade space now as they did then. This understanding changes the meaning of emptiness at the deepest level. In classical intuition, emptiness is defined by subtraction. Remove matter, and what remains is void. In quantum field theory, emptiness is defined by configuration. The vacuum state is the reference point from which excitations are measured. It is not the deletion of content, but the baseline arrangement of fields. The conceptual shift is subtle yet decisive. Historical development clarifies how this picture emerged. In the 1920s, the quantization of the electromagnetic field resolved inconsistencies between classical wave theory and atomic emission spectra. Later, the unification of quantum mechanics with special relativity required treating particles as field excitations to maintain causality and locality. The Dirac equation predicted antiparticles as natural features of the electron field. When Carl David Anderson discovered the positron in 1932, it confirmed that fields contain within them the potential for both matter and antimatter. The discovery was not an addition to emptiness. It was an unveiling of what the field structure already allowed. Spin also reinforces this field-centered view. The spin of particles is tied to representations of the Lorentz group, the mathematical description of space-time symmetries in special relativity. Fields transform under these symmetries in specific ways. A scalar field, like the Higgs field, transforms differently from a vector field, like the electromagnetic field, and differently again from a spinor field, like the electron field. These transformation properties determine observable quantities such as angular momentum, conservation, and selection rules in atomic transitions. Spin is not attached to isolated objects. It is encoded in field behavior. As this perspective settles, one realization becomes unavoidable. If particles are localized vibrations and fields are the enduring substrate, then what we once called empty space is a dynamic yet well-defined ground configuration. The absence of particles does not imply the absence of structure. It signals that the fields are resting in their vacuum state. That state carries properties measurable through interactions, scattering, and cosmological observation. If the vacuum is only a lowest energy configuration, what physical evidence proves that its subtle activity can generate measurable forces in complete isolation from matter? If empty space contains nothing at all, why do two uncharged metal plates placed a few micrometers apart in a perfect vacuum begin to move toward each other with a measurable force? This is not a thought experiment. It is a laboratory result. The phenomenon is known as the Casimir effect, and it transforms the quantum vacuum from an abstract concept into a physical influence detectable with precision instruments. In 1948, Hendrik Brookt Gerhard Casimir, working at Philips Research Laboratories in the Netherlands, was studying interactions between neutral molecules. He considered how quantum electrodynamics describes electromagnetic fields even in their vacuum state. At that time, zero-point energy was already a formal part of quantum theory, but its physical consequences were still debated. Casimir realized that when two perfectly conducting plates are placed parallel to each other at very small separations, the allowed electromagnetic modes between them are restricted compared to the modes outside. The vacuum is not silent. It supports fluctuations of the electromagnetic field. By changing the boundary conditions, the plates alter which fluctuations are permitted in the gap between them. The reasoning is subtle but precise. In quantum field theory, Each electromagnetic mode behaves like a harmonic oscillator with a minimum energy even in the absence of photons. When plates are far apart, the spectrum of allowed wavelengths in the space between them is continuous. When the plates are extremely close, only wavelengths that fit exactly between them are permitted. Longer wavelengths cannot exist in that narrow region. Outside the plates, no such restriction applies. This difference in allowed modes produces a difference in energy density between the interior and exterior regions. Energy density differences correspond to pressure. The vacuum fluctuations outside exert slightly more radiation pressure than those inside the gap. The result is a net force pushing the plates together. Casimir derived a formula predicting that the force per unit area would increase sharply as the separation decreases, varying inversely with the fourth power of the distance. If the plates are separated by 1 micrometer, the predicted pressure is small but measurable with sensitive equipment. At 100 nanometers, it becomes significantly stronger. The dependence on separation is so steep that reducing the distance by a factor of 10 increases the force by a factor of 10,000. For decades, the prediction remained experimentally challenging. Perfectly parallel plates are difficult to align at submicrometer separations. Tiny dust particles, surface roughness, and electrostatic charges can overwhelm the expected signal. Early attempts in the 1950s and 1960s produced results with large uncertainties. The force was suspected, but not yet established with confidence. The challenge was not theoretical elegance. It was engineering. A major breakthrough came in 1997 when Steve K. Lamoureux at Los Alamos National Laboratory conducted a high-precision experiment using a torsion pendulum setup. Instead of 2 flat plates, he used a spherical surface and a flat plate to reduce alignment difficulties. By measuring minute angular deflections caused by the force between the surfaces, he obtained results within a few percent of Casimir's prediction. For the first time, vacuum fluctuations were no longer confined to equations. They exerted a measurable force in a laboratory. Subsequent experiments refined the measurement. Umar Mohideen and Anushri Roy at the University of California, Riverside, performed atomic force microscope measurements in 1998, reducing separation distances to below 200 nanometers. Their data agreed with theoretical predictions after accounting for finite conductivity and surface roughness. Later, experiments introduced micro-electromechanical systems to measure the force with even greater control. The agreement between theory and experiment has reached high precision, confirming that the effect arises from quantum electrodynamics rather than stray electrostatic interactions. The vacuum contributes a force that cannot be explained by classical electromagnetism alone. It is important to clarify what the Casimir effect does and does not demonstrate. It does not imply that virtual particles are colliding with plates like tiny billiard balls. That language, though common in simplified descriptions, can obscure the deeper structure. The effect emerges from boundary conditions imposed on quantum fields. When the allowed modes of a field are altered, the ground state energy shifts. The measurable force reflects that shift. The vacuum is not empty in the classical sense. It is a configuration of fluctuating fields sensitive to geometry. The scale of the force provides insight into its origin. At separations of 1 micrometer, the pressure is roughly 1 millipascal. For plates of 1 square centimeter area, this corresponds to a force of about 10 to the minus 7 newtons. That is small, but well within the range of modern force sensors. As separations approach 100 nanometers, the force increases dramatically. These values are consistent with calculations derived from quantum field theory without introducing adjustable parameters beyond material properties. Precision confirms interpretation. The Casimir effect also depends on material properties. Real conductors are not perfect reflectors at all frequencies. Finite conductivity modifies the spectrum of allowed modes. Temperature introduces additional contributions from thermal fluctuations. Detailed theoretical models incorporate these corrections, and experiments have confirmed their influence. The agreement between measured data and corrected theory strengthens confidence that the underlying mechanism is accurately understood. The vacuum responds to boundaries in a predictable way. Interest in the Casimir effect extends beyond fundamental physics. In microelectromechanical devices, components separated by nanometer-scale gaps can experience Casimir forces that cause stiction, unwanted sticking due to attractive forces. Engineers designing nanoscale systems must account for these quantum forces. The effect, therefore, bridges abstract theory and practical technology. It is a reminder that quantum field behavior influences systems far removed from cosmic scales. Although NASA and the European Space Agency do not conduct Casimir experiments in orbit as primary missions, space-based instrumentation benefits indirectly from the precision of quantum electrodynamics. Atomic clocks aboard Global Positioning System satellites depend on corrections derived from quantum theory. Spectroscopic measurements of distant galaxies rely on atomic transition frequencies influenced by vacuum fluctuations. The consistency of laboratory quantum effects underpins confidence in astrophysical interpretation. Field theory connects tabletop experiments to cosmological observation. The story behind Casimir's insight carries quiet significance. Casimir was investigating forces between neutral molecules when he encountered calculations suggesting an interaction even without charge. The realization that vacuum fluctuations could produce measurable attraction was not widely accepted at first. It required careful reasoning and years of technological development to validate. The long interval between prediction and confirmation illustrates how theoretical clarity often precedes experimental capability. Persistence was essential. The Casimir effect also invites deeper questions about zero-point energy. The energy difference between inside and outside the plates is finite and measurable, yet the absolute vacuum energy density remains formally divergent in naive calculations. Renormalization procedures subtract the infinite baseline, leaving only differences that influence forces. This technique is standard in quantum field theory and has been validated across countless experiments. The Casimir force arises not from the total vacuum energy, but from changes in allowed modes. Geometry shapes quantum behavior. It is worth emphasizing that the effect depends on the electromagnetic field alone. Other quantum fields contribute analogous phenomena in principle, but the electromagnetic contribution dominates at accessible scales. The vacuum fluctuations of the electromagnetic field are constrained by conducting boundaries, and that constraint produces force. This direct relationship between boundary conditions and measurable pressure highlights the physicality of the vacuum state. Alter the geometry, and the vacuum responds. Over time, experiments have explored variations, including repulsive Casimir forces using specially engineered materials and fluid environments. These configurations modify how electromagnetic modes propagate between surfaces. Observing both attractive and repulsive versions reinforces that the effect arises from controlled manipulation of field modes rather than accidental charge interactions. The vacuum behaves consistently under varied conditions. The Casimir effect stands as one of the clearest demonstrations that the quantum vacuum is not merely a theoretical placeholder. It produces force, measurable and repeatable, at micrometer and nanometer scales. Its existence supports the broader framework of quantum field theory, within which fields persist even in the absence of particles. Empty space is structured by the laws governing those fields. If boundaries can reshape the electromagnetic ground state, what subtle fingerprints might vacuum fluctuations leave on the internal structure of atoms themselves? If empty space has no structure, why did a hydrogen atom in 1947 reveal an energy difference that the most successful relativistic equation of its time said should not exist? The discrepancy was small, measured in megahertz, yet it carried profound weight. It meant that even in the absence of external fields, the vacuum itself was influencing atomic structure. Hydrogen is the simplest atom. It contains one proton and one electron. Because of this simplicity, it became the testing ground for quantum mechanics in the 1920s. The Schrödinger equation predicted its energy levels with remarkable accuracy. Later, in 1928, Paul Adrien Maurice Dirac introduced a relativistic equation for the electron that incorporated spin naturally and explained fine structure effects in hydrogen's spectrum. Dirac's theory predicted that certain pairs of energy levels, specifically the two states known as 2s1/2 and 2p1/2, should have exactly the same energy. According to the Dirac equation, these states were degenerate. For nearly 2 decades, no experiment contradicted this prediction. Spectroscopy had not yet reached the resolution necessary to test such subtle distinctions. Then came a new experimental approach during and after the Second World War. Radar research had advanced microwave technology dramatically. High-frequency cavities, stable oscillators, and precision detection systems became available for laboratory science. Willis Eugene Lamb and Robert Curtis Rutherford recognized that these tools could probe atomic transitions that were previously inaccessible. Microwave spectroscopy offered a new level of sensitivity. In 1947, Lamb and Rutherford directed a beam of hydrogen atoms through a microwave field tuned to induce transitions between the two p1/2 and two s1/2 states. They used a magnetic field to separate states and detected changes through electron emission when atoms were quenched. What they observed was unexpected. The 2s1/2 state was slightly higher in energy than the 2p1/2 state by about 1000 MHz, equivalent to roughly 4 microelectron volts. The Dirac equation alone could not account for this difference. The result became known as the Lamb shift. It was small in absolute terms, yet precise enough to demand explanation. The question was immediate. What interaction was missing from the theoretical description? The hydrogen atom had been treated as an electron bound to a proton through the electromagnetic force described by classical fields quantized in the simplest way. But the vacuum had not been fully included as an active participant. Julian Schwinger, Richard Feynman, and Shinichiro Tominaga developed a more complete formulation of quantum electrodynamics in the late 1940s. Their framework incorporated interactions between the electron and fluctuations of the electromagnetic field even in its ground state. In this picture, the electron does not move in isolation. It interacts with virtual photons that arise from vacuum fluctuations permitted by the uncertainty principle. These interactions slightly modify the electron's effective energy levels. The vacuum alters the atom from within. The explanation can be described without equations. The electron in hydrogen occupies orbitals characterized by probability distributions around the proton. In the 2s1/2 state, the electron's probability density is non-zero at the nucleus. In the 2p1/2 state, the probability density at the nucleus is zero. Because vacuum fluctuations modify the electromagnetic field at extremely small distances, states that sample the region near the proton more strongly are affected differently. The interaction between the electron and vacuum fluctuations shifts the energy of the S state slightly more than that of the P state. The degeneracy predicted by Dirac is lifted. This correction is not an arbitrary adjustment. It emerges from a systematic expansion in quantum electrodynamics known as perturbation theory. The electron emits and reabsorbs virtual photons. These temporary processes alter its self-energy. The shift calculated by Schwinger and others matched the experimental value within experimental uncertainty. The agreement validated the renormalized theory and confirmed that vacuum fluctuations have measurable consequences. A difference of 1000 MHz reshaped atomic theory. The historical context carries weight. The Lamb shift was announced at the Shelter Island Conference in 1947, where many leading physicists gathered to discuss post-war developments. The experimental result forced a re-examination of quantum electrodynamics. The earlier formulation had encountered divergences that seemed insurmountable. The necessity of explaining the Lamb shift motivated the development of renormalization procedures that would later become central to the Standard Model. A subtle spectral line influenced the architecture of modern physics. Microwaves were essential to the measurement. Optical spectroscopy lacked the resolution to separate such closely spaced energy levels. Microwave radiation, with wavelengths on the order of centimeters and frequencies in the gigahertz range, could drive transitions between nearly degenerate states with high precision. By scanning the microwave frequency and observing resonance peaks, Lamb and Rutherford identified the exact energy difference. The experimental uncertainty was small enough to challenge theory directly. Technology opened a window that theory had not anticipated. Subsequent experiments refined the measurement further. Precision spectroscopy using atomic beams and later laser techniques confirmed the Lamb shift with increasing accuracy. Modern measurements account for additional corrections, including proton finite size effects and higher-order quantum electrodynamics contributions. The theoretical framework continues to match observation at extraordinary precision. The hydrogen atom remains one of the most precisely tested systems in physics. The vacuum contribution is embedded in every refined calculation. The implications extend beyond hydrogen. Similar radiative corrections affect all atoms. Fine structure splittings, hyperfine interactions, and anomalous magnetic moments all incorporate vacuum fluctuation effects. The electron's anomalous magnetic moment, measured with extraordinary precision in Penning trap experiments, agrees with quantum electrodynamics predictions, including vacuum contributions to many decimal places. Such agreement reinforces the interpretation that these fluctuations are not conceptual devices, but elements of measurable reality. Atomic structure is inseparable from the vacuum. Observational astronomy depends on these corrections as well. Spectral lines observed by space telescopes, including those operated by the National Aeronautics and Space Administration and the European Space Agency, are interpreted using atomic models grounded in quantum electrodynamics. The James Webb Space Telescope analyzes emission and absorption lines from hydrogen and other elements in distant galaxies. The reliability of these interpretations rests on laboratory-confirmed atomic theory, including vacuum-induced shifts. Cosmic measurements inherit the precision of atomic experiments. The Lamb shift also clarified the meaning of virtual photons. These are not directly observable particles. They represent internal lines in Feynman diagrams, bookkeeping tools in perturbative calculations. Yet the effects associated with them, such as energy level shifts, are observable. The distinction is subtle. One does not detect virtual photons individually. One measures the consequences of their permitted interactions. The hydrogen atom serves as a laboratory demonstration of this principle. The vacuum leaves fingerprints without revealing its individual quanta. It is instructive to consider what would happen if vacuum fluctuations were absent. The two S1/2 and two P1/2 levels would remain exactly degenerate. Precision spectroscopy would reveal no shift. The Dirac equation would stand unmodified in that respect. The absence of the Lamb shift would contradict decades of high-precision measurement. Instead, the presence of the shift confirms that quantum electrodynamics must include the vacuum as an active element in calculations. The data compel inclusion. The Lamb shift marks a turning point. Before 1947, the vacuum could be treated as a passive background in many atomic calculations. After the measurement, it became clear that even the simplest atom contains contributions from field fluctuations in empty space. The vacuum is not an external arena. It is part of the system. Hydrogen carries within it the imprint of quantum emptiness. As the evidence accumulates from atomic beams, microwave cavities, and modern laser spectroscopy, one conclusion grows increasingly precise. The vacuum state influences measurable quantities at scales of microelectron volts. That influence is not hypothetical. It is recorded in resonance frequencies and spectral lines. A shift too small to notice without careful instrumentation became the confirmation that emptiness possesses structure. And once a single hydrogen atom reveals that the vacuum modifies its internal energy, the next challenge presses forward with quiet insistence. If light itself carries no charge, how can the vacuum respond as though it were a medium capable of polarization? If light carries no electric charge, how can empty space respond as though it were a material capable of polarization? The question reaches into the structure of quantum electrodynamics and touches the meaning of charge itself. In classical electromagnetism, polarization describes how a material rearranges its internal charges when an external electric field is applied. Atoms in a dielectric shift slightly. Positive and negative charges separate by tiny distances, producing an internal field that partially screens the applied one. The material does not create new charges. It repositions those already present. In quantum field theory, something analogous occurs even in what we call vacuum. The key lies in the concept of vacuum polarization. According to quantum electrodynamics, the vacuum state permits fluctuations consistent with the uncertainty principle. Among these fluctuations are temporary electron-positron pairs. These are not particles propagating freely through space. They are short-lived disturbances in the electron field and its antiparticle counterpart. When a strong electromagnetic field is present, such as near a charged particle, these fluctuations become slightly biased. The vacuum rearranges its internal activity in response to the field. To build intuition, consider an everyday dielectric such as glass placed between the plates of a capacitor. When an electric field is applied, electrons in the glass shift slightly relative to their nuclei. This displacement reduces the effective field within the material. The dielectric constant quantifies how much screening occurs. The result is that the measured electric force between charges changes compared to what would be observed in empty space. Replace the glass with vacuum, and classical theory predicts no screening at all. Quantum theory revises that expectation. In quantum electrodynamics, the electromagnetic field interacts with charged fields, including the electron field. Even in the vacuum state, the possibility of electron-positron pair creation influences how the field propagates. Near a positive charge, the vacuum fluctuations arrange so that negative virtual charges are slightly more likely to be found closer to the source, while positive virtual charges are slightly displaced outward. This arrangement resembles polarization in a material. The effect is subtle yet calculable. The charge appears partially screened by the vacuum itself. This screening modifies how the electric force behaves at different distances. At large separations, the effective charge appears smaller because vacuum polarization reduces the field strength. At very short distances, the screening is reduced and the effective charge increases. Experiments in high-energy scattering confirm this scale dependence. When electrons are scattered at higher energies corresponding to shorter distances, the measured interaction strength differs from that at low energies. This phenomenon is known as the running of the coupling constant. The vacuum reshapes how charge is felt. The theoretical description involves corrections to the photon propagator in quantum electrodynamics. Instead of traveling unmodified, the photon interacts with virtual electron-positron pairs. These loops alter the effective field. The mathematics can be expressed through integrals over momentum space, but the physical meaning can be conveyed simply. The vacuum modifies the propagation of electromagnetic influence. The correction is not optional. It is required for agreement with experiment. Precision spectroscopy confirms it. Consider again the hydrogen atom. Beyond the lamp shift discussed earlier, vacuum polarization contributes additional small corrections to energy levels. These corrections influence fine structure splittings and hyperfine interactions. Modern spectroscopic measurements of hydrogen and muonic hydrogen achieve extraordinary precision. Theoretical calculations, including vacuum polarization, match experimental values within tight uncertainties. When discrepancies arise, they prompt deeper investigation into proton size or higher-order effects, not dismissal of vacuum contributions. The agreement is quantitative. Scattering experiments at particle accelerators provide another line of evidence. At the European Organization for Nuclear Research and other facilities, electron-positron collisions are analyzed across a wide range of energies. The measured cross-sections depend on the effective electromagnetic coupling. As energy increases, the observed strength changes in accordance with predictions that include vacuum polarization. Without these corrections, theoretical curves would diverge from data. With them, agreement is restored. The vacuum acts as a medium, with measurable response properties. The story of vacuum polarization traces back to early developments in quantum electrodynamics. In the 1930s, calculations of radiative corrections encountered infinities. The electron's self-energy diverged without careful treatment. The renormalization program developed in the 1940s allowed these divergences to be handled systematically. Within that framework, vacuum polarization emerged as a finite, testable correction after renormalization absorbed the infinities into redefined physical parameters. The procedure was controversial at first. It was later recognized as consistent and predictive. Theoretical persistence led to empirical validation. Strong electromagnetic fields reveal the effect more dramatically. In extremely intense fields, such as those near heavy nuclei or produced in high-energy collisions, vacuum polarization contributes measurable shifts in atomic levels. Experiments with highly charged ions, where an electron orbits a nucleus with many protons, show corrections that must include vacuum polarization to match observation. The stronger the field, the more pronounced the effect. The vacuum response scales with field strength. Astrophysical environments provide indirect confirmation. Near magnetars, neutron stars with magnetic fields exceeding 10 to the power of 10 Tesla, theoretical models predict vacuum birefringence, a phenomenon in which the vacuum behaves as a birefringent medium due to polarization effects. Observations of polarized light from magnetars have shown signatures consistent with these predictions. While direct laboratory fields cannot yet match those magnitudes, the alignment between theory and astrophysical measurement strengthens confidence in the underlying physics. Space becomes a testing ground for quantum electrodynamics. It is important to avoid misunderstanding. Vacuum polarization does not imply that space is filled with permanent particles. The electron-positron pairs involved are transient fluctuations constrained by quantum uncertainty. They cannot be isolated or detected directly. Their influence appears only through corrections to measurable quantities. The distinction matters. The vacuum remains the lowest energy state of fields, yet its structure allows interaction. The medium is defined by law, not by substance. The concept of polarization also clarifies the running of the fine structure constant. At everyday scales, the electromagnetic interaction is characterized by a dimensionless number approximately equal to 1 divided by 137. At higher energies, measurements reveal a slightly different effective value. The change is small but consistent with vacuum polarization calculations. The coupling strength evolves with energy scale. This evolution is not imposed by hand. It arises from field interactions within the vacuum. The numbers agree across independent experiments. Precision experiments on the anomalous magnetic moment of the electron and the muon further confirm these corrections. Theoretical predictions include contributions from vacuum polarization loops. The measured values match theoretical calculations to extraordinary accuracy for the electron and reveal small deviations for the muon that continue to be studied. The framework remains robust. The vacuum's polarizable character is embedded in the calculation of these moments. The smallest measured discrepancies test the deepest aspects of field theory. When light passes through a region influenced by vacuum polarization, it still carries no charge. The photon remains electrically neutral. The modification arises because the electromagnetic field interacts with charged fields present in the vacuum configuration. The response does not belong to the photon as a particle. It belongs to the field structure of space. The neutrality of light is preserved, while the vacuum mediates the interaction. The cumulative evidence leaves little room for metaphor. Vacuum polarization is not a poetic description. It is a calculable correction derived from quantum electrodynamics and confirmed in spectroscopy, scattering, and astrophysical observation. The effect is small in everyday conditions, yet measurable in controlled experiments and high-field environments. Empty space responds according to precise equations. If the vacuum can screen electric charge and modify atomic structure through polarization, then its internal energy must also obey strict rules of stability. That tension moves forward quietly. If zero-point energy and polarization are real, why does the vacuum not unleash enormous effects across the universe? If the quantum vacuum carries zero-point energy and fluctuating fields, why does ordinary space remain calm enough for atoms to form, molecules to bind, and chemistry to proceed without catastrophe? The question is not dramatic exaggeration. It arises directly from quantum field theory. When physicists calculate the energy associated with vacuum fluctuations, the raw mathematical expression appears enormous. Yet the universe we observe is stable, cool on average, and governed by delicate atomic interactions. Something in the structure of the theory prevents the vacuum from acting as an uncontrolled energy source. To understand this stability, it is necessary to distinguish between two kinds of energy. One is extractable energy, energy that can drive change because a system can transition to a lower state. The other is baseline energy, a reference level inherent to the definition of the vacuum state. In quantum mechanics, every oscillator possesses a minimum energy that cannot be removed without violating the uncertainty principle. This minimum does not represent fuel waiting to be tapped. It represents the floor of allowed configurations. No lower state exists into which the system can fall. The quantum vacuum is defined as the lowest energy configuration of all fields. It contains no real particles, yet it retains zero-point contributions. Crucially, because it is already the minimum, there is no process within ordinary quantum electrodynamics that can release this baseline energy. A system can emit radiation if it occupies an excited state. The vacuum is not excited, it is the ground configuration. Without a lower state, no energy can be extracted. This principle can be illustrated through a simpler system. Consider an atom in its ground state. It does not radiate spontaneously because it has no lower electronic level to which it can transition. The electron can emit energy only when it drops from a higher state. In the same way, the vacuum cannot decay into a state of lower energy unless a deeper configuration exists. Within the standard model as currently understood, the vacuum state for most fields appears stable on timescales far exceeding the age of the universe. Stability is built into the definition. The appearance of enormous vacuum energy arises when summing contributions from all possible modes of quantum fields. Each mode contributes a small baseline energy, and when integrated over all wavelengths, the naive total diverges. Renormalization addresses this issue. Conceptually, renormalization recognizes that only differences in energy have measurable consequences in non-gravitational contexts. Infinite or extremely large constant offsets can be absorbed into redefined parameters, leaving finite predictions for observable quantities. The procedure is not arbitrary. It is constrained by experiment. In the late 1940s, Julian Schwinger, Richard Feynman, and Sein-Ichiro Tomonaga independently developed renormalized quantum electrodynamics. Their work allowed infinities associated with self-energy and vacuum fluctuations to be systematically removed by redefining charge and mass in terms of measured values. The success of this approach was confirmed by its extraordinary agreement with precision experiments. The anomalous magnetic moment of the electron, for example, matches theoretical predictions including radiative corrections to many decimal places. Renormalization turned apparent instability into predictive consistency. The conceptual core of renormalization is subtle but clear. Physical measurements determine the values of quantities, such as charge and mass, at specific energy scales. The infinite baseline contributions are not observable directly. What is observable are shifts relative to that baseline. By anchoring the theory to experimental inputs, predictions become finite and testable. The vacuum energy that remains in non-gravitational calculations does not manifest as explosive radiation because it represents an overall constant rather than a gradient driving motion. No gradient, no force. Many vacuum effects that are observable are indeed subtle. The Casimir force between plates separated by 1 micrometer is on the order of millipascals. The Lamb shift in hydrogen is measured in megahertz, corresponding to microelectron volts. Vacuum polarization modifies charge interactions by small fractions that become apparent only in high-precision scattering experiments. These are delicate corrections, not overwhelming energies. Their smallness is not accidental. It reflects the structure of quantum field interactions at accessible scales. The reason these effects remain small lies in coupling strengths and energy scales. The electromagnetic coupling constant is approximately 1 divided by 137 at low energies. This small dimensionless number ensures that higher-order quantum corrections are progressively suppressed. Even when vacuum fluctuations contribute, their influence is moderated by this coupling. Only in extreme conditions, such as near-heavy nuclei or in high-energy collisions, do corrections become more pronounced. Everyday space operates in a regime of modest interaction strength. Observations across astronomy reinforce this picture of stability. The cosmic microwave background, measured by the National Aeronautics and Space Administration and the European Space Agency, reveals a universe whose average temperature today is about 2.7 Kelvin. Intergalactic space is exceedingly dilute. If vacuum energy behaved like accessible thermal energy, this calm background would be impossible. Instead, atomic transitions and molecular bonds proceed according to quantum electrodynamics without runaway effects. The structure of atoms observed in distant galaxies through spectroscopy matches laboratory predictions. Chemistry survives because vacuum corrections are constrained. The role of gravity introduces a different dimension to the discussion. In general relativity, energy density influences spacetime curvature. A constant vacuum energy density acts like a cosmological constant, contributing to the expansion dynamics of the universe. Observations of accelerated expansion, inferred from Type Ia supernova measurements in the late 1990s and later confirmed by cosmic microwave background data, indicate a small positive effective vacuum energy density. The magnitude is approximately 10 to the minus 26 kilograms per cubic meter when expressed as mass density equivalent. This value is tiny compared to naive quantum field estimates. Here the tension becomes numerical rather than explosive. Quantum field theory calculations of vacuum contributions, when extended without modification to gravitational coupling, suggest values many orders of magnitude larger than observed. Yet the universe expands gently, not violently. The discrepancy remains one of the most significant open problems in theoretical physics. However, even this mismatch does not imply that vacuum energy burns space locally. The observed effect is a gradual acceleration over billions of years. Subtle on cosmic scales, invisible on atomic scales. The fact that gravity is sensitive to absolute energy density, while non-gravitational physics responds only to differences, explains why vacuum energy becomes relevant primarily in cosmology. In atomic physics, renormalization absorbs constant offsets. In cosmology, the constant influence is spacetime geometry. The measured acceleration is small enough that galaxies, stars, and planetary systems remain stable over billions of years. The vacuum does not ignite matter because it does not provide a pathway to lower energy in ordinary interactions. Stability persists under constraint. Another factor reinforcing stability is symmetry. Many fields possess symmetries that protect the vacuum configuration. Gauge invariance in electromagnetism ensures that certain vacuum contributions cancel when calculating physical observables. Lorentz invariance requires that the vacuum look the same in all inertial frames. These symmetries restrict the form of allowed corrections and prevent arbitrary energy release. Mathematical consistency enforces physical restraint. Historical perspective highlights how unexpected this stability once seemed. Early quantum field calculations appeared to produce uncontrollable infinities. The fear that the theory might predict catastrophic vacuum behavior was not unfounded. The development of renormalization transformed that concern into a structured framework. As Richard Feynman later reflected on quantum electrodynamics, he remarked that it was the most accurate theory ever developed. The precision of its predictions rests on careful handling of vacuum contributions rather than their elimination. Control replaced chaos. The absence of vacuum combustion is therefore not mysterious once definitions are precise. Zero-point energy belongs to the baseline of fields. It is not stored energy waiting to be released. Observable effects arise from differences, boundaries, and interactions. The vacuum state is stable because it is defined as the minimum allowed by the theory under current conditions. Atomic structure, molecular chemistry, and macroscopic matter rely on this stability. The universe does not burn because there is nowhere lower for the vacuum to fall. Yet one domain remains where the baseline cannot be dismissed so easily. When absolute energy density couples directly to spacetime curvature, renormalization does not simply subtract it away. The question then shifts from local stability to cosmic scale influence. If the vacuum's baseline energy shapes the expansion of the universe, why does its value appear so small compared to theoretical expectation? If quantum field theory assigns energy to empty space, why is gravity not overwhelmingly strong at every point in the universe? The question exposes one of the most serious numerical tensions in modern physics. On one side stand the calculations of quantum vacuum energy. On the other stand astronomical observations of the universe's expansion. The two do not align, not by a small margin, but by an astonishing range of orders of magnitude. In general relativity, energy density influences spacetime curvature. The equations formulated by Albert Einstein in 1915 include a term known as the cosmological constant. This term behaves like a uniform energy density filling space. If vacuum energy exists, it should contribute to that constant. The logic appears direct. Quantum fields possess zero-point energy. Zero-point energy is a form of energy density. Energy density curves spacetime. Therefore, vacuum energy should affect cosmic expansion. The reasoning is clear. The outcome is perplexing. When physicists estimate the contribution of vacuum fluctuations to energy density using quantum field theory, they consider all possible modes of all fields up to a cutoff scale where new physics might emerge. Even if that cutoff is chosen conservatively, the resulting energy density is extraordinarily large. The exact number depends on assumptions, but typical estimates exceed the observed cosmological energy density by more than 100 orders of magnitude. This is not a minor discrepancy. It is the largest known mismatch between theory and observation. Astronomical data provide the comparison. In the late 1990s, Two independent teams studying Type Ia supernovae, led by Adam Guy Rees and Saul Perlmutter, found evidence that the universe's expansion is accelerating. The brightness of distant supernovae indicated that galaxies are receding faster over time than expected from gravity alone. Subsequent measurements from the Wilkinson Microwave Anisotropy Probe and the Planck satellite refined the cosmological parameters. The effective energy density associated with this acceleration corresponds to approximately 10 to the minus 26 kilograms per cubic meter. It is small, but not zero. This measured value behaves as though space itself contains a constant energy density. In the framework of general relativity, it can be modeled by a cosmological constant. The tension arises because quantum field theory seems to predict a vastly larger value. If the naive theoretical estimate were correct, spacetime curvature would be so extreme that the universe would have expanded or contracted violently shortly after its origin. Galaxies would not have formed. Atoms would not have assembled. The universe we observe would not exist in its current form. Steven Weinberg articulated this conflict clearly. He distinguished between what he called the old cosmological constant problem and the new cosmological constant problem. The old problem asks why the vacuum energy predicted by quantum field theory does not gravitate with the enormous magnitude suggested by simple calculations. The new problem asks why the small observed value is not exactly zero. Why does the cosmological constant have the tiny positive value inferred from supernova and cosmic microwave background data? Both questions remain unresolved. The historical context adds depth. Einstein originally introduced the cosmological constant to achieve a static universe model. After Edwin Hubble's discovery of cosmic expansion in 1929, Einstein reportedly referred to the constant as his biggest blunder, though the exact wording is debated. Decades later, observational evidence revived the term in a new role. It now appears not as a device to hold the universe static, but as a component driving accelerated expansion. The constant returned with new significance. Its magnitude, however, resists explanation. Theoretical approaches have attempted various resolutions. Some propose that unknown symmetries cancel vacuum contributions almost exactly. Supersymmetry, if realized in nature, would cause contributions from bosons and fermions to partially cancel. Yet experimental searches at high-energy colliders have not confirmed supersymmetry at accessible energy scales. Other approaches suggest that vacuum energy is not a simple constant, but arises from dynamic fields evolving over cosmic time. Observational data from Planck and large-scale structure surveys constrain such models tightly. None have eliminated the tension completely. Anthropic reasoning has also entered the discussion. If many regions of a broader multiverse possess different vacuum energy values, observers would naturally arise only in regions where the value permits galaxy formation. Steven Weinberg argued that anthropic considerations might predict a cosmological constant not much larger than the one observed. This line of reasoning remains controversial. It does not derive the value from fundamental principles. It identifies selection effects. The debate continues. From an observational standpoint, the evidence for accelerated expansion is robust. Type Ia supernovae act as standardizable candles because their intrinsic luminosity correlates with the shape of their light curves. By comparing observed brightness to intrinsic luminosity, distances can be inferred. When combined with redshift measurements, the expansion history can be reconstructed. The data indicate acceleration beginning several billion years ago. Cosmic microwave background measurements independently support a flat universe with a dominant, smooth energy component. Multiple lines of evidence converge. The smallness of the observed value deepens the puzzle. It is not merely that the theoretical estimate is too large, it is that the actual number is finely tuned relative to typical quantum scales. Expressed in terms of energy density, the observed value corresponds to roughly 10 to the -9 joules per cubic meter. Compared to the energy density associated with nuclear processes or particle masses, this is minuscule. Yet it dominates cosmic dynamics on the largest scales. Small in magnitude, large in consequence. The contrast between local and cosmic behavior highlights the distinction introduced earlier. In atomic and laboratory physics, constant vacuum energy offsets can be absorbed through renormalization because only energy differences influence measurable quantities. In gravity, absolute energy density matters. Spacetime curvature responds to the total. This difference explains why vacuum energy does not disrupt chemistry, but influences cosmic expansion. The same baseline that is invisible in spectroscopy becomes central in cosmology. Context determines visibility. Precision cosmology continues to test the constancy of this energy density. Observations from baryon acoustic oscillations, gravitational lensing surveys, and large-scale galaxy distributions provide independent constraints. So far, the data are consistent with a constant value over cosmic time. No strong evidence for evolution has emerged. The simplicity of a constant term matches observation remarkably well. The simplicity of its value remains unexplained. The cosmological constant problem, therefore, stands at the intersection of quantum field theory and general relativity. It signals that our understanding of vacuum energy in a gravitational context is incomplete. The mismatch does not invalidate either framework within its tested domain. Quantum electrodynamics predicts laboratory results with extraordinary accuracy. General relativity describes planetary motion, gravitational waves, and black hole mergers observed by detectors such as the Laser Interferometer Gravitational Wave Observatory. Yet their combination at the level of vacuum energy reveals a gap measured in powers of 10. Many physicists regard this tension as a clue pointing toward deeper structure. It suggests that a future theory unifying quantum fields and gravity may contain mechanisms not yet recognized. Until such a framework is established, the cosmological constant problem remains open. The observed acceleration is real. The theoretical expectation is enormous. The two coexist in unresolved tension. Gravity is not enormous everywhere because the vacuum's gravitational effect is small, but why it is small remains one of the central questions in modern physics. What observation forced the scientific community to accept that a smooth, pervasive energy component is driving cosmic acceleration? What measurement was powerful enough to overturn decades of expectation and reveal that the expansion of the universe is not slowing down, but speeding up? In the late 1990s, observations of distant Type Ia supernovae provided that measurement. The implication was immediate and unsettling. The universe was not merely expanding, it was accelerating. Gravity, which had been expected to slow cosmic expansion, appeared to be losing the competition to a smooth, pervasive energy component now called dark energy. To understand how this conclusion emerged, it is necessary to begin with Type Ia supernovae themselves. These stellar explosions occur in binary systems where a white dwarf accretes matter from a companion star. A white dwarf is supported by electron degeneracy pressure and cannot exceed a mass of approximately 1.4 solar masses, known as the Chandrasekhar limit. When the mass approaches that threshold, carbon fusion ignites explosively throughout the star, producing a thermonuclear detonation. Because the explosion occurs near a consistent mass, the intrinsic luminosity of type Ia supernovae is remarkably uniform. This uniformity allows them to serve as standardizable candles. A standard candle is an object whose intrinsic brightness can be determined independently of its distance. By comparing intrinsic brightness to observed brightness, astronomers calculate how far away the object must be. Type Ia supernovae are not perfectly identical, but their light curves reveal correlations between peak luminosity and the rate at which brightness declines. By measuring how quickly the light fades, astronomers correct for variations and determine the true luminosity with high precision. Distance becomes measurable across billions of light years. In parallel, redshift measurements provide the rate at which distant galaxies are receding. Redshift arises because the expansion of space stretches the wavelength of light traveling through it. The larger the redshift, the more the universe has expanded since the light was emitted. Combining distance and redshift allows reconstruction of the expansion history. If gravity dominated the universe's energy content, expansion would gradually decelerate. Distant supernovae would appear slightly brighter than in a constant expansion model because they would be closer than expected in an accelerating universe. That was the expectation. Two independent teams pursued this program. The Supernova Cosmology project, led by Saul Perlmutter, and the Higgs Supernova Search Team, led by Brian Schmidt with Adam Guy Rees as a key member, gathered observations throughout the 1990s. They identified and monitored dozens of distant type Ia supernovae. The measurements required careful calibration, correction for interstellar dust, and precise photometry using ground-based telescopes and the Hubble Space Telescope operated by the National Aeronautics and Space Administration. The analysis demanded statistical rigor. When the data were compiled, the result contradicted prior expectation. The distant supernovae were dimmer than predicted in a decelerating universe. Dimmer meant farther away than expected for their redshift. The expansion had been slower in the past than it is now. In operational terms, acceleration means that the rate at which galaxies separate increases with time. The scale factor describing cosmic size grows more rapidly than in a universe governed solely by matter. Gravity was not halting expansion. Something was opposing it. Adam Guy Rees later reflected on this moment in his Nobel lecture, describing how quickly the implication reorganized the cosmic energy budget. A smoothly distributed energy component was required to account for the data. This component would not clump like matter. It would exert negative pressure, leading to repulsive gravitational behavior in general relativity. The cosmological constant, once set aside, returned as the simplest explanation. The term introduced by Albert Einstein re-entered cosmology under new conditions. Independent evidence reinforced the supernova results. Measurements of the cosmic microwave background by the Wilkinson Microwave Anisotropy Probe and later by the Planck satellite provided precise constraints on the universe's geometry and composition. The data indicated a spatially flat universe, meaning total energy density equals the critical density. Observations of galaxy clusters and large-scale structure accounted for only about 30% of this density in the form of matter, both baryonic and dark. The remaining 70% required a smooth component consistent with dark energy. Multiple methods converged on the same conclusion. The effective energy density associated with this component corresponds to approximately 10 to the minus 26 kilograms per cubic meter. Although small in everyday terms, it dominates the large-scale dynamics of the universe because it does not dilute as matter does. As the universe expands, matter density decreases in proportion to the volume increase. A cosmological constant remains constant per unit volume. Over billions of years, this constant component becomes dominant. Acceleration emerges gradually. Further confirmation came from baryon acoustic oscillations, patterns imprinted in the distribution of galaxies that reflect sound waves in the early universe. Surveys such as the Sloan Digital Sky Survey mapped these patterns and measured distances at different epochs. The data aligned with a model including dark energy consistent with a cosmological constant. Gravitational lensing studies also supported the same framework. Consistency across independent probes strengthened confidence. It is important to clarify what acceleration means physically. It does not imply galaxies move through space faster in the conventional sense. Instead, the metric describing space expands at an increasing rate. The separation between distant galaxies grows more rapidly over time. This acceleration is detectable through the relationship between redshift and luminosity distance. The data show that for a given redshift, supernovae are farther away than they would be in a universe without dark energy. The expansion history records the influence. The cosmological constant remains the leading suspect because of its simplicity. In general relativity, adding a constant energy density term naturally produces accelerated expansion. Alternative models introduce dynamic scalar fields or modifications to gravity, but current observational constraints favor a constant equation of state parameter consistent with -1, as expected for vacuum energy. Data from the Planck mission combined with supernova measurements limit deviations tightly. Simplicity and observation align. The story behind the discovery reflects both caution and surprise. Initial analyses were scrutinized for systematic errors. Dust extinction, evolutionary effects in supernova progenitors, and calibration uncertainties were examined. Independent teams confirmed the findings using different techniques. The convergence of results from separate groups increased confidence. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Guy Rees were awarded the Nobel Prize in Physics for the discovery of accelerated expansion. The observation reshaped cosmology. The connection to vacuum energy emerges through general relativity. If the vacuum possesses a small constant energy density, it behaves gravitationally as dark energy. The cosmological constant problem discussed earlier concerns why this value is so small compared to quantum field estimates. Observationally, however, the value is what it is. It governs expansion today. The vacuum may push the cosmos apart, not through explosive force, but through persistent, uniform influence. The effect accumulates over billions of years. Space telescopes continue to refine measurements. The James Webb Space Telescope observes distant supernovae at higher redshifts, extending the baseline of expansion history. Upcoming missions aim to measure dark energy parameters with even greater precision. The goal is to determine whether the equation of state parameter deviates from -1 at any level. So far, the data are consistent with a cosmological constant. Precision increases. The mystery remains. Dark energy therefore rests on empirical foundation. Type Ia supernovae act as distance markers. Redshift provides recession velocity. The mismatch between expected and observed brightness revealed acceleration. Complementary data confirmed a dominant smooth component. The cosmological constant re-emerged as the simplest interpretation. The vacuum's role in cosmic expansion became observational fact rather than theoretical speculation. Could the vacuum we inhabit be only a temporary configuration rather than the absolute lowest state allowed by nature? If the vacuum defines the structure of everything, what if the state we call stable is only temporary? The possibility is not a thought experiment created for drama. It arises directly from quantum field theory and from measurements of the Higgs boson mass at the Large Hadron Collider operated by the European Organization for Nuclear Research. The question is precise. Does the Higgs field sit in an absolutely stable minimum of its potential energy, or in a metastable one that only appears stable over cosmic timescales? To approach this carefully, we begin with what physicists mean by a vacuum state. In quantum field theory, the vacuum is not empty. It is the lowest energy configuration of all fields. Each field has an associated potential energy landscape. The shape of that landscape determines which configurations are stable. Imagine not a particle moving in space, but a field defined at every point in space, taking on a value that minimizes its energy. That minimum defines the vacuum. However, some potential energy landscapes contain more than one minimum. One minimum may be deeper than another. A system can sit in a higher minimum if separated from the lower one by an energy barrier. This condition is called metastability. The configuration is stable against small disturbances, but not absolutely stable against quantum tunneling. Over sufficiently long timescales, a transition to the lower state is possible. The concept is mathematically well defined. The Higgs field provides a concrete case. Discovered in 2012 at the Large Hadron Collider, the Higgs boson mass was measured to be approximately 125 gigaelectronvolts. Combined with precise measurements of the top quark mass, these values determine the shape of the Higgs potential at high energies. Calculations performed by multiple research groups indicate that, within current uncertainties, the Higgs field may lie near the boundary between absolute stability and metastability. The numerical proximity is striking. If the Higgs vacuum is metastable, then at extremely high field values the potential energy could dip lower than the current state. Quantum tunneling could, in principle, nucleate a bubble of true vacuum. Inside that bubble, the Higgs field would take on a different value. Particle masses and coupling constants would change. The laws governing atoms would no longer be the same. The bubble would expand at nearly the speed of light. The process is called vacuum decay. It is important to emphasize that such a transition, if possible, is predicted to be extraordinarily unlikely within the lifetime of the universe. Calculations of the decay rate depend sensitively on the Higgs mass, the top quark mass, and physics beyond the standard model. Current estimates suggest a lifetime far exceeding the age of the universe, which is approximately 13.8 billion years. Observationally, cosmic history itself constrains the scenario. The universe has passed through extreme conditions. Shortly after the Big Bang, temperatures exceeded 100 billion Kelvin. Particle collisions at those energies were common. If the vacuum were highly unstable, such conditions might have triggered a transition. The fact that galaxies, stars, and atoms exist today implies that either the vacuum is absolutely stable or metastable, with a decay time vastly longer than cosmic history. Empirical survival sets bounds. Research continues to refine these bounds. Measurements of the Higgs boson properties at the Large Hadron Collider aim to reduce uncertainties in coupling strengths. Future colliders are proposed to measure the top quark mass with greater precision, since small shifts in that value significantly alter stability predictions. The sensitivity is not marginal. A change of a few hundred mega-electronvolts can move the vacuum from stable to metastable in theoretical calculations. Precision becomes decisive. The idea of multiple vacuum states is not speculative invention. In quantum field theory, scalar fields naturally admit such structures. The mathematics describing tunneling between minima was developed in detail by Sidney Coleman and collaborators in the 1970s. The formalism calculates the probability per unit volume, per unit time for a bubble to nucleate. The calculation does not rely on metaphor. It uses established quantum principles extended to field configurations. The framework is rigorous. One might ask, what observational evidence would count as confirmation of metastability? Direct observation of vacuum decay is not feasible if the event occurs at nearly light speed. However, indirect evidence would arise if precise measurements placed the Higgs and top quark masses firmly in the metastable region with negligible uncertainty. Additionally, discoveries of new particles could modify the Higgs potential at high energies, either stabilizing or destabilizing it. The vacuum's fate depends on physics not yet fully measured. Cosmology adds further constraints. Inflationary models of the early universe involve high field values. If the Higgs potential dips lower at extreme energies, interactions during inflation might have pushed the field into that region. The absence of such a transition suggests that inflationary dynamics either avoided dangerous field excursions or that new physics stabilized the vacuum. Observations of the cosmic microwave background from the Planck satellite limit inflationary parameters and thereby indirectly inform vacuum stability discussions. Cosmology and particle physics intersect. The Standard Model alone appears delicately balanced. Some researchers interpret this near criticality as coincidence. Others consider it a clue. The proximity to instability may indicate underlying principles yet to be discovered. Supersymmetry, additional scalar fields, or modified high-energy behavior could reshape the Higgs potential. None have been experimentally confirmed so far. The question remains open within established theory. It is worth clarifying that metastability does not imply imminent catastrophe. Quantum tunneling probabilities for such transitions, given current parameters, are extraordinarily small. The expected lifetime of a metastable vacuum in these calculations vastly exceeds not only the current age of the universe, but also the timescale over which stars will burn out. The risk is theoretical, not immediate. Yet the conceptual significance is profound. The vacuum is not merely background. It determines particle masses through the Higgs field's non-zero value. It governs interactions. If alternative minima exist, then the constants of nature depend on which minimum is realized. The distinction between false vacuum and true vacuum becomes a question about the deepest structure of physical law. Stability is not assumed. It is computed. The Large Hadron Collider experiments, including ATLAS and CMS, continue to measure Higgs production channels and decay modes. Any deviation from Standard Model predictions could signal new contributions altering the potential at high energies. So far, measurements align closely with expectations. This consistency narrows possibilities but does not eliminate metastability within current error margins. The margin is small, yet significant. In this framework, vacuum decay represents a boundary condition on cosmic history. The fact that the universe has persisted for billions of years implies strong constraints on the decay rate. Astrophysical events such as neutron star mergers, gamma-ray bursts, and high-energy cosmic ray collisions have occurred without triggering a transition. These observations indirectly reinforce stability or extremely long metastability timescales. Nature provides repeated tests. The vacuum, therefore, may not be unique. It may be one of several allowed configurations. The one we inhabit appears stable on observable timescales. Whether it is the absolute lowest energy state remains a matter of calculation and measurement. The Higgs field anchors this inquiry because its potential shape defines the vacuum structure in the Standard Model. The stability of the universe is tied to its parameters. And if the vacuum's configuration determines not only particle masses but possibly the structure of spacetime itself, then a deeper question stands ahead. Could space and time emerge from vacuum physics, rather than merely provide the stage upon which it unfolds? If the vacuum has measurable energy, measurable fluctuations, and measurable consequences, what if space and time themselves are not fundamental but emerge from that same underlying structure? This is not a poetic extension of earlier ideas. It arises directly from the tension between quantum field theory and general relativity. Quantum theory treats fields as fundamental entities defined on spacetime. General relativity treats spacetime itself as dynamic, curved by energy and momentum. When both are pushed to their limits, the question becomes unavoidable. What is more fundamental, the stage or the actors? John Archibald Wheeler introduced an image that remains influential. He proposed that at extremely small scales, spacetime may not be smooth, but instead exhibit violent fluctuations. He called this picture quantum foam. The term refers to distances near the Planck length, approximately 1.6 times 10 to the minus 35 meters. At that scale, quantum uncertainty in energy could produce fluctuations in geometry itself. The smooth fabric described by Einstein's equations would dissolve into a fluctuating microstructure. The concept is mathematically motivated. The Planck scale emerges from combining three constants. The gravitational constant, the speed of light, and Planck's constant define a characteristic length, time, and energy where quantum effects of gravity become unavoidable. The Planck time is roughly 5.4 times 10 to the minus 44 seconds. Below that duration, classical spacetime loses operational meaning because quantum fluctuations in geometry are expected to dominate. These numbers are not speculative. They follow directly from dimensional analysis of established constants. Testing such scales directly is beyond current experimental capability. To probe the Planck length with particle collisions would require energies around 10 to the 19 giga-electron-volts, far beyond the reach of the Large Hadron Collider. That machine accelerates particles to several tera-electron-volts, which is many orders of magnitude smaller. Direct access remains technologically impossible. Because direct probes are unattainable, physicists search for indirect evidence. One approach examines high-energy astrophysical observations. If spacetime possessed a granular structure at tiny scales, it might cause slight modifications in how photons propagate over cosmological distances. Gamma-ray bursts traveling billions of light-years provide long baselines. Experiments such as the Fermi Gamma-ray Space Telescope have analyzed arrival times of photons with different energies. So far, no statistically significant deviation from Lorentz invariance has been observed. Constraints tighten. Gravitational wave observations offer another window. The Laser Interferometer Gravitational Wave Observatory and the Virgo detector measure space-time distortions from merging black holes and neutron stars. The waveforms match predictions from general relativity with remarkable precision. Any quantum gravity corrections at observable scales must therefore be extremely small. The smooth space-time model continues to pass tests. Cosmic microwave background measurements also provide constraints. The Planck satellite mapped temperature and isotropies with high resolution. These fluctuations reflect conditions when the universe was approximately 380,000 years old. Inflationary models sometimes predict imprints of quantum gravitational effects in primordial perturbations. Current data are consistent with a nearly scale-invariant spectrum, with no clear signature of Planck scale modifications. The evidence remains indirect. Theoretical frameworks attempt to unify quantum mechanics and gravity. Loop quantum gravity proposes that space-time is quantized, composed of discrete units of area and volume. String theory proposes that fundamental entities are one-dimensional strings whose vibrational modes produce particles and whose consistency requires additional dimensions. Both approaches aim to describe how space-time geometry emerges from deeper degrees of freedom. Neither has yet produced experimentally confirmed predictions at accessible energies. The search continues. One central issue is whether space-time is fundamental or emergent. In some approaches inspired by holography, space-time geometry may arise from patterns of quantum entanglement. The anti-de Sitter and conformal field theory correspondence, developed in the late 1990s, suggests that gravitational dynamics in a higher dimensional space can be equivalent to a non-gravitational quantum field theory defined on its boundary. This duality implies that geometry may be encoded in quantum correlations. Geometry becomes derivative rather than primary. If spacetime emerges from quantum structure, then the vacuum state of quantum fields may carry more information than previously assumed. Entanglement entropy across regions of space relates to geometric quantities such as area. Black hole thermodynamics reinforces this connection. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This relationship, first identified by Jacob Bekenstein and Stephen Hawking, links gravitational physics to quantum statistical behavior. Area replaces volume. Testing these ideas requires measurable consequences. Some models predict deviations in black hole evaporation rates, modifications in gravitational wave dispersion, or imprints in early universe cosmology. Precision measurements from observatories such as the Event Horizon Telescope, which image the shadow of a supermassive black hole, confirm general relativity's predictions within current resolution. No deviation has yet been observed. The window remains narrow. Quantum foam, if real, would influence spacetime at ultra-short scales, but average out at macroscopic distances. Just as molecular motion averages into smooth fluid flow, microscopic geometry might average into classical spacetime. Detecting such structure would require sensitivity to cumulative effects over vast distances or energies approaching the Planck scale. Present instruments, including those operated by the National Aeronautics and Space Administration and the European Space Agency, provide ever-improving resolution, yet remain far from direct Planck scale access. Technology advances incrementally. The absence of detected deviations does not eliminate the possibility of microstructure. It constrains its scale and form. Any viable theory of quantum gravity must reproduce the successes of general relativity and quantum field theory at accessible scales while resolving their incompatibility at extremes. That compatibility requirement severely limits theoretical freedom. Consistency becomes the guiding principle. The deeper implication concerns the role of the vacuum. Earlier discussions showed that vacuum fluctuations affect atomic spectra, generate measurable forces, and influence cosmic expansion. At the quantum gravity frontier, the vacuum may determine the fabric from which spacetime itself arises. The distinction between background and dynamics blurs. The vacuum may not merely fill space. It may participate in defining what space is. The conceptual shift is significant. John Archibald Wheeler once said, "Space-time tells matter how to move. Matter tells space-time how to curve." If space-time is itself emergent from quantum vacuum structure, that relationship may represent only an effective description. Beneath it may lie degrees of freedom not yet identified experimentally. The challenge is to translate that possibility into predictions that can be tested. Without testable consequences, theory remains incomplete. Current research programs aim to identify such consequences. High-precision interferometry, cosmic polarization measurements, and improved gravitational wave detectors seek subtle anomalies. The James Webb Space Telescope studies the earliest galaxies, constraining inflationary models and thereby limiting quantum gravity scenarios. Particle accelerators search for deviations from standard model behavior that might hint at new structure. Each dataset refines boundaries. The journey from zero-point energy to quantum foam reveals a continuous thread. The vacuum is not an absence. It has measurable structure, measurable influence, and possibly measurable geometry. Whether space and time themselves arise from this structure remains an open scientific problem. The question is not resolved. It is being tested, step by step. The investigation continues. Thank you for following this exploration with patience and attention. Your time and focus give meaning to these long examinations of the universe's foundations. Wherever you are listening from, may the rest of your night unfold steadily and peacefully. Good night.